Welcome to the series of 4 review lectures for the course Introduction to Mathematical Physics. The first review, lecture 1A, will cover the material up to the end of differentiation. Review lecture 1B will look at everything up to the end of integration. And review lectures 2A and 2B cover the back end of the course. Review lecture 2A covers the material from the extracted notes from reading assignment 4, and review lecture 2B will cover the extracted notes from reading assignment 5. So I'll just briefly go over the table of contents for review lecture 1A, and most of the material that will basically be covered in the subsequent slides is just sort of going to give you a quick review. If you want more details, just basically refer to the slides, lectures, notes from earlier in the course. So we started with looking at the sketching of surfaces, and we had different approaches that we could use to help us assist in understanding what a 3D object looks like. Traces, level curves, and cylinders are the things that we basically looked at. And these are things you should become familiar with because they were certainly used in the back end of the course when we dealt with reading assignment 5. And we looked at the definition of a limit and looked at the various approaches taken to prove if a limit exists or does not exist. That led us then into the definition of continuity of multivariable functions. And then we looked at the notion of partial derivatives and also direct derivatives. Partial derivatives exist in the context of multivariable calculus, but they did not exist when we were dealing with single variable calculus. And then that naturally led to the notion of differentiability when we're dealing with multivariable calculus. Then we looked at basically how we would apply the chain rule and used a number of examples to sort of illustrate the process. One of the more important things is the use of the chain rule, and when we have to do implicit differentiation. Again, implicit meaning that the function is not z as a function of x, y, but it's written basically in terms of x, y, z is equal to 0. And then we looked at the notion of a directional derivative and also the definition of a gradient. And these were both new concepts which only apply when we're dealing with multivariable calculus. And we looked at the application basically of using all the information that we had obtained up to that point, in particular multivariable Taylor series expansion. In first year, we basically dealt with Taylor expansion of single variable functions, and here we extended to the notion of multivariable functions. The first thing that comes into mind would be, for instance, the definition of a tangent plane when we're dealing with basically a three-dimensional object. We all looked at sensitivity analysis, basically using Taylor series expansion, and this was applicable to time-independent physical problems. And lastly, we looked at small signal analysis, which basically was the time dependency when we're dealing with physical problems, typically when we're modeling real systems. All right, one of the things basically that we learned in this course was how to sketch objects in 2D and 3D. And the tools that you learned to sketch 3D are displayed in the table below. So they were traces, level curves, and cylinders. So what is a trace? It's a cross-section of an object in 3D. The most common traces were the XY plane, XZ plane, and YZ plane. And the trace of a 3D object is generally a curve in 2D. It could be a point as well, as will be displayed in the graph below. So if we were to take this equation here, which is y equals x squared over 6 plus z squared over 16, if we'd chosen y equal to 0, that would have been xz trace, in which case the only solutions would be x equals z equals 0, which would be in the black dot that you see there. In this case, if we were to hold y constant at a value of 0.25, that would be equivalent to a trace, but with a different value of y. Then basically what we'd be doing is graphing the equation of an ellipsoid, which is this black line that you see here. So these are two specific examples that were considered here. For level curves, what is a level curve? It's a projection of the 3D object for a given value of z projected onto the XY plane. And these types of projections are commonly used, for example, in topographical maps to depict elevation, or in maritime weather charts to predict the barometric pressure profiles in storms. So for example, if we were to take this function here, which is Gaussian, and for a specific value of z, you'll be plotting y as a function of x. Then you would change the value z and plot it again. So if we do that, we find that we end up with a series of circles of specific radius corresponding to different values of z. And so judging by how z is altered, if z is in equidistant values, then what we would see here is a distance between individual circles that could be similar, could be compressed, it could sort of spread out, which tells you something about the rate of change. Now, this is typically what you might see when you're looking at a topographical map. All right, last is what we meant by cylinders, and these are objects that extend to infinity in a particular direction, in which case the description of the shape of the object is a function of only two variables, and the third variable is assumed to be a member of the real number set. So for example, if I wrote x squared plus y squared equals 1, it would imply that z is an element of R if I know that this is in fact a 3D object. So for example, x squared plus 4y squared equals 16. This is basically an equation of ellipse if we let z equals 0, that's in the xy plane. But since z can be anything, it's like extruding this ellipsoid that you see in red along the z-axis, and so you essentially see a scaffold which is in the form of a cylinder but with ellipsoid shape. Next thing we did was to look at limits in the multivariable case, but restricted ourselves to more or less two variables. And there were only two issues that came up. One was, how do you go about proving a limit exists or it does not exist? And so there were basically a few techniques that we basically explored. If you want to prove the limit exists, then try to prove this assertion using specific techniques such as factorization, algebraic conjugate, substitution of new variables, and basic theorems for analytical functions. So that was basically our toolbox. On the other hand, to prove the limit does not exist, also called the two-path test, it uses a contrapositive approach so that you can find at least two paths for which the limit is different than the limit does not exist. And typically in this case, you use the substitution of variable technique for the two-path test. All right, so definition of continuity. Again, this is just going to be very brief. You'll basically have to show that all of the three conditions are satisfied. So that means that if, for instance, condition 1 is satisfied and condition 2 is not satisfied, there's no need to move on to proving that condition 3 is satisfied. So all must be satisfied. We also looked at continuity of composite functions. And so basically we looked at the function g and the function of x to prove continuity for both, and then more or less we were able to show that the function as a whole was continuous. All right, so then we looked at partial derivatives, and this was a new material, so we defined what we meant by partial derivative. We are dealing only with two variables, so we can take a function and take its derivative with respect to x, which would be f partial x, and then do the same thing for f partial y. And this is a standard definition that you used in Calculus 1 when you talk about derivatives. But in this case, you would be holding one of the parameters fixed, and the other one would be varied. So next thing that we looked at was the equality of mixed partial derivatives. So in this case, basically, if you, for instance, were to take the derivative with respect to y followed by x, or the other way around, then the question is that what is the relationship between the two? Well, if fxy and fyx are continuous, then fxy is equal to fyx. And you could extend this basically if you're taking triple differentiation. So for example, in the statement below, fxyx equals fxxy equals fyxx, all partial derivatives basically would have to be continuous, in which case all those three combinations shown there would be equivalent. All right, and then the question came down to what we meant by differentiability. We're dealing with multivariable calculus. And so here basically you have the theorem 15.5 for conditions for differentiability. And then you could also apply the contrapositive argument, which in some cases was much easier to work with. So that's why both are indicated. And then another useful theorem, theorem 15.6, was that if it's differentiable, it implies continuity. And then a contrapositive argument basically could also become useful as well. Again, it depends on the nature of the problem that you're trying to solve. All right, one thing we considered in the course was the chain rule. So let's just look at an example again. We covered this in an earlier lecture. We have a picture here which describes some relationship in economics between productivity and labor, productivity and capital, and productivity and resources. Labor depends on unemployment, capital depends on interest rate, and resources depends on time. And so what we're interested in knowing is to what extent productivity depends on unemployment, interest rate, and time. And so first of all, we could draw this out in terms of a chain diagram like this and like this. So you can see this is a chain, U being at the bottom, I being at the bottom, and T being at the bottom. And these are nodes representing L, K, and R along here. Now, we would express this in functional form as some function of labor, capital, and resources, where individually the labor depends on unemployment rate, capital on interest rate, and resources on time. If I were now to take the partial derivative, take the derivative of P with respect to U, and I have to make a distinction between what is a partial and what is a direct derivative. So if we look at this diagram, along each one of these links, basic from P to L, this will be a derivative, but this will be a partial derivative. Why? Because there's a bifurcation. This splits into three. So each one of these links will be partial derivatives. P with respect to L, P with respect to K, and P with respect to R. In this case, L goes to U directly, K goes to I directly, and R goes to T directly. There is no splitting, and there's nothing else. It's just a direct connection. And so these would be direct derivatives, dl du, dk di, and dr dt. So from P to U would involve the product of this derivative times this derivative, which would be partial derivative of P with respect to L and direct derivative of L with respect to U. Similarly, you can do the same thing for the remaining two links. We found that we could use the chain rule for differentiation, particularly if you're dealing with an implicit function. So for instance, if you have z as a function of x as a function of y of x, but you're not necessarily given it y of x, but nevertheless, if you were able to put y in terms of x, then this expression is perfectly valid. All right, and then we're going to assume that z is a level curve, which means z equals constant. So if we apply the chain rule to this expression, then we'd have dz dx, which is a direct derivative, is df dx, which is a partial derivative, df dy dx, and the equivalent diagram is shown over on this side. But since z is a constant, it's a level curve, that means this is equal to 0. From this, therefore, we're able to basically compute dy dx. If this were an implicit form, you would not be able to extract y of x, and therefore you would not be able to compute dyx. And so this approach allows us to compute dy dx given an implicit function. We can extend this basically to more than two variables. So for instance, if we have x, y, and z, but z is a function of x and y, then w now becomes a level surface. If we apply the chain rule, we can obtain the value for dz dx and dz dy. So if we do w dx and break this out, this is df partial x plus dfz dz dx. And again, because it's a level surface, w is a constant, so the derivative of this will be equal to 0. So you can solve for dz dx partial. Similarly, you can do it for dy dy partial. And again, because it's a level surface, the derivative is equal to 0. And the diagram here basically would be representing these computations that I've shown here. All right, so then the next thing we did was the directional derivative and gradient definition. Why directional derivative? Because depending on which direction you go, you see a different slope. And so a directional derivative basically just says the actual physical slope if you're moving in a particular direction. Right? And so that's why I mentioned here the slope of the curve at a given point in the direction of the curve traversal. All right. So you're basically charting a path down some surface, but if you project that path onto the xy plane, that's the direction of the traversal that we're referring to.
And so we went through in quite detail. These are expressions that we had. I'm not going to go into further detail since I don't have any diagrams at this point. And so we had two different ways of looking at the problem. One is the parameterized representation of the contour, or the direction in which we're traveling, and an explicit representation. In the parameterized representation, we basically would represent x and y in terms of parameterization variable t, but in the explicit representation, we would represent y in terms of x. And so effectively, we end up with slightly different expressions, but if you go through to the end, you find effectively you get the same expressions, no matter which approach you take. Now this term here, we call the gradient, and we basically defined it as such, and f partial x, f partial y. And so if we write now the directional derivative, it's nothing more than the dot product, or the projection of the gradient vector in the direction in which you are traveling. That is the projection on the xy plane. And so this could be represented as grad f, and this is a unit vector, u. This can also be written in terms of the magnitude of the gradient, the magnitude of u, which is 1 cosine phi, and then depending on what the angle is between the direction you're going and the direction of the gradient vector, which is the direction in which the slope is a maximum, right? We were able to look at different scenarios. So if it's perpendicular, which is cosine 0, which means you're walking around the hill, which means the slope is equal to 0. And so this is something we covered in great detail in an earlier lecture. Then we basically looked at tangent planes, but we extended this notion to other applications, in which case we were dealing with physical problems. And we didn't necessarily call them tangent planes, but mathematically that's what they were. And so we looked at a multivariable Taylor series expansion of a particular function. And so we looked at this as being one approach for tangent planes, and also defining the equation of an arbitrary vector that is orthogonal to the gradient at a point on the surface. So two different approaches we used to determine a tangential plane. For the multivariable Taylor series expansion method, we took the function, right, which is in this case two variables, and we expanded outwards. This is in matrix form. So C would be evaluated at the point AB. This would be the gradient vector dot D, where D was just the difference vector between x and the established values at a given point, y and y minus b. That's the gradient vector. This would be evaluated at the position of interest. And then we left with the second order term, which we wrote in this form. This is D, again, this vector. So this would be in row form, and this would be in column form. And this was a matrix which we called the Hessian matrix. We didn't make use of this, but if you were looking at, for instance, determining min and max for basically a two-variable function, then you would end up basically investigating the properties of this Hessian matrix. Of course, we did not have time to do that in this course because we have something called a reading week now. All right, the vectors, the gradient f is basically what we're calculating. The d of transpose, which you're basically taking this row vector and making it to a column vector, would look like this. The other approach was to find the equation of the tangent plane at a point on the surface, and so this basically would matter of just considering position x, y, z at any point on the tangent plane and create the vector between this point and the point ABC on the surface defined by fx, y, z equals 0. This is basically just written here in implicit form. Then the gradient vector dot x minus a, y minus b, z minus c. So this is an arbitrary vector, basically which has its tail positioned at the point of interest on the surface. This is perpendicular to the surface at the given point, x equals a, y equals b, and z equals c. If you want a tangential plane, then this vector and the vector perpendicular to the surface must be 90 degrees with respect to each other, in other words, orthogonal. So that means this dot product must be equal to 0. Under these conditions, basically, when you solve this equation, you get an equation that will be linear in x, y, and z, which is by definition going to be the tangential plane. So this is basically the two approaches that we took when we dealt with tangent planes. All right, we then looked at a sensitivity analysis. And so here what we were interested in knowing is that if you're at a given point and you perturb it slightly in any given direction, direction X and direction Y, how does the value Z change? And so this would be a differential. So Z minus C would be the change on Z. How is infected by changes in X and changes in Y, which meant that all we need to do is compute the partial derivative with respect to X, evaluated at X equals A, Y equals B, and partial with respect to Y evaluated at X equals A and Y equals B. And so we went through this process. And so effectively, we could do calculations which we call sensitivity analysis. We also find that quite often it's simpler to write these equations in per unit form so that basically we compress the number range that we're working with. And so a per unit analysis would require us to divide through by Z throughout, but also everything in this system would have to be in per unit form. So delta X can be converted to per unit by dividing by X and then multiplying through by X. Here we would divide through by Y and multiply through Y. So here, for instance, the Z is common to all. But here we have an X here and an X here. This is going to be per unit. This is per unit, right? And so if we take this now and carry through, right, then we will find that we end up with a simplified values. These end up becoming constants that have been calculated, right? And these will be also constant would be calculated. And so what we end up with then is an expression between per unit Z is some constant time per unit X plus some constant time per unit Y. And so this sometimes is simpler to use rather than have to work with basically the raw numbers.
All right, so the last thing we discussed in this section would be the multivariable Taylor series expansion as applied to small signal analysis. And we showed that for any set of system, we have typically equations that define the operation of the system as a whole. We have state space equations, which involve state variables, which are the ones that are tied to the derivatives that you see on the left. So in this case, there's two state variables, x1 and x2, and these differential equations or state space equations depend on the variables on the right-hand side of x1, x2, as well as any input variables. In this case, there are two input variables, u1 and u2. And then there'll be output equations that depend on the state variables and the input variables. Notice here that we have one differential equation is nonlinear. Why? Because x1 basically is squared. And we have one output equation nonlinear. Why? Because it's u2 to the power of 4. So we describe basically the small signal analysis model in terms of two issues. One is determine these equilibrium conditions. And that means we need to understand what is the stable value, equilibrium value for x1 and also for x2. And we obtain that by taking and setting the derivatives to 0 and then solving these equations. u1 and u2 are given. These are static values for input variables. And we're trying to determine what are the static values for x1, x2, designated as x capital subscript 1 and x capital subscript 2. So this is a matter of solving a nonlinear equation in general, and from which we obtain x1, x2. And then the small signal model involves basically small perturbations in the state variables, which depend on the perturbations of state variables and the input variables. And there'll be a matrix in front of here, which is determined. It's a Jacobian matrix, which involves the partial derivatives with respect to x1 and x2. And partial derivatives here with respect to u1 and u2. We also have the output equation. So we have the equilibrium point, which is determined by substituting the steady state variables for x1, x2, u1, u2, 1, u2 in the output equations, from which we obtain the steady state or equilibrium values for the output variables. If we want the small signal equations for the output, then this involves small perturbations, the output being related to small perturbations in the state variables and the input variables. And again, we end up with matrices involving partial derivatives with respect to the state variables and partial derivatives with respect to the input variables. And these are pre-computed. These all depend on the operating point. In other words, these derivatives are evaluated at specific points, which would be x1, x2, u1, and u2. Now, you could convert these equations to per unit form, in which case all state variables, input variables, and output variables and time need to be divided by normalization values for the respective quantities. This just makes computations a little bit easier because you compress the number range. All right, so this concludes Review 1A. Thank you for listening.